Well, hello, Cal State Straub. This is exciting. We're finally into chapter 13, the last chapter that covers items for the AP exam this year, since 14 and 15 will not be on it. So, phew, we got to make it through this week, and then we've gained all the knowledge we need for the test in a couple of weeks. So, I'm gonna start you off with a practice for the warm-up. This is an old AP question from 2002, but you can see it's asking you to create a confidence interval for a proportion. So since this is something that could show up on your exam in a couple of weeks, I'd like for you, whether it's our final or the AP exam, like for you to review that. This was from chapter 10, where we learned that. And then I want you to answer question B. Put those answers into Edpuzzle for me. I'll probably be asking for your conclusion there. Please notice that in A, it asks you to give an interpretation of the confidence interval and an interpretation of the confidence level. And we were talking about these two things being different things to report on. So if you need to look at your notes to do that, I'm certain you need to know the difference between those two, probably for the AP exam as well. So make sure you answer both things. One of the things that I shared with those of you who came to video conference sessions, I told you one of the tips from the AP test writers was that you read the question and you answer the question. So you read this carefully and see that you have two things to talk about, not just one. The biggest mistake students make is they go ahead and say, we are 95% confident that, and then they stop and don't see that you also need to interpret the level. So just go ahead and take care of that, and then we'll come back and look at my answers. Not sure why that came up. All right, so here's what we should have been doing. Your procedure should be, remember, you always list your procedure for any kind of inference, whether it's confidence interval or significance testing. This one was a 1 proportion Z interval. Okay. You should have named your population and your parameter here. I just kind of noted a few things quickly on my key, but our parameter is the true proportion of U.S. adults who would respond, make some major changes. Okay. And so U.S. adults is our population. All right, then our SRS was given here. This was a proportion, so we need to check our NP hat and N times 1 minus P hat. Remember, this is confidence interval. We don't have a P null. If it was a significance test, we'd be using P null there, not P hat, but it's confidence interval. So P hat it is. Both of those are greater than 10, so that clears. And then our large number 10N situation is definitely more adults than 260 in the United States. Okay. I did the formula method of doing our P hat plus or minus Z star for 95% times your SE formula for proportions and get the interval. So interpreting the confidence interval is this: we are 95% confident the true proportion of US adults is between 36 and 41, almost 42%, who would say make some major changes. Now I put the confidence level down here at the bottom. In the long run, this is what the level means. In the long run, 95 out of 100 times, the interval made with this procedure of the same sample size, which I should put 1,026, okay? I guess that would have been 10,260 U.S. adults up there, right? Okay, sorry. Will contain the true proportion of adults who say make some major changes. So keep that separate. If you need to pause and make sure you have these written well, I think it's a good idea. You'll probably see that again. Then part B asked you, what about this statement was misleading? And basically, yes, 39% want major changes, but 19% want to completely overhaul the system. That's another choice. When you add those two together, basically 58% really truly want major changes, more than half. But this is how, and I know, I don't know about you guys, but on this coronavirus stuff, we see data thrown at us every single day. And people make data look like what they want. Yes, they're not lying that 39% said they want major changes. but they are not telling the whole picture by leaving out the 19% who want even more than that to happen. And so really more than half of the people on that survey want to see changes to the system. And they're making it look like less. So be careful when we read our data. This is one of those great questions for that. Okay. All right, we're going to go to today's notes on two sample proportions. Let me get this into, there we go, presentation mode. Okay, we're going to start off section 1 is doing a 2 sample test with means, and then section 2 is 2 sample testing with proportions, for proportions. So this is going to be all about means today, and the next, I've broken this into 2 sessions of notes. All right, so far with inference testing, we have done, for means, just focusing on means right now, we have done a single sample or a 1 sample t-test. We have done paired t-test, and that's where you have 1 sample, but each subject gets both treatments, a before and an after, things like that, like you had on your test for chapter 12, where you compared the scores before and after they took a course, right? Okay, but it's the same sample. The other type of inference testing is, let me get my, oops. Okay, sorry about that, guys. Oh, everything disappeared there. 2 samples from 2 separate populations. That's what this chapter is about. This is going to be 2 sample t-test. There is 2 sample z-test as well, although that's very rare, and we're going to talk about it. I'll show you both, but most of these will be run as 2 sample t's. Notice they're 2 independent samples from 2 separate populations, okay? And I'll show you some examples. Okay. So when we're doing 2 sample problems, our goal is to compare the responses to 2 treatments or to compare the characteristics of the same variable of 2 different populations. We have separate samples from 2 distinct populations, and the responses of the 2 groups have to be independent of each other. Like one group cannot have an effect on the other group's results. They have to be completely independent. That's an added condition here that we have to look at. So we're going to go through, just like before, your state, plan, do, conclude. Your state's still going to be your populations and your parameters. Now you have to list 2. Okay, I'm being a little silly here, but you're going to be doing population for the first sample, parameter for the first, population for the second. Okay. So we do that, and then for our, I'm going to show you the way to state the hypotheses in just a minute. But checking conditions is the same 3, SRS, normal, and independent. SRS, they have to both be randomly selected. You have to state both were random samples, okay? Normality, they both have to be normal. So in the mean situation, CLT will work for us here and has to be greater than than 30 for each of them to claim CLT. Okay. Independence, now we have just a couple. We have with added statements you have to make. You're still doing the 10N for both. So you have to run 10N for the first population and 10N for the second. But then you have to also state that we're assuming these 2 samples have no influence on each other. They're independent of each other. Okay? For example, if you were doing children and their parents and doing them separately, those might not be independent because the parents might have influence on their children's way they answer questions or whatever in the samples. So that's not considered clearing the conditions for a 2 sample test. Okay. All right. So let's just go a little bit more. Remember, these are not paired in any way. This is not a paired T. And this is the thing that I'm almost certain is going to be on your AP exam. They want you to know the difference between a paired t-test and a 2 sample t-test because that's tricky. Is it 2 separate populations that you're comparing? 2 distinct samples. Okay. If it is, then it's a 2 sample t-test. If it is not, if you're pairing them. It's the same people and you're doing a before and an after, or it's the same kind of boots and you're doing a left shoe and a right shoe. That's a paired test, okay? Not completely different populations, okay? Here's an interesting thing about two sample testing is that they don't have to be the same size. The N of one could be different than the N of the other. However, getting equal sizes as much as possible is actually better for the results and better for when we're trying to look at normality in our formulas. So it's a better idea to have that, but they don't have to be. Okay? All right, what about stating the hypotheses now? So here's how I want to spend some time. This is a little different. Okay, I've named my two populations A and B. When I'm doing a problem, sometimes I use letters that go with the problem, like if it was comparing freshmen to seniors, I might do mu sub F and mu sub S to keep them very straight in my head. It doesn't matter, but what you're in your state, you will be stating that. You'll be saying mu sub A, okay, is the true mean, whatever number of hours or whatever. Mu B is the true mean number of hours for population B. So you'll be setting those up in your state very clearly and showing your notation at the beginning. Okay, I just like to use letters that go along with the problem to keep my mind clear on it. But you don't have to. You can just use A and B all the time. So your HO for this, remember, the null hypothesis is that there is no difference, no change. So in these guys, the mu of the first is the same as the mu of the second. They are equal. Okay, there's no difference between them. Sometimes we see that written this way as well, the second way here with where my pointer is, that the difference between them is 0. Okay, no difference at all. Okay, now that's if we're doing a two-sided test. Okay, two-sided test, we'll be doing that. Okay, now the HA, I'm sorry, I don't mean here, but down here, the HA for a two-sided test is that they're not equal to each other. There is a difference. And so sometimes that could be written, and I'll show you in a minute. Well, why don't I show you now? Nope, I guess it wasn't there. Mu sub A minus mu sub B is not equal to 0 is another way that could be written. Okay? Or if it's one-sided test, then this should go here. This word two-sided right here should be down here, not there. Sorry about that, guys. Okay, so now you either say, it tells you that you're testing to see if this population did better than this or more than this, or if this population did less than. So reading the context of the question determines whether you're doing a two-tailed or a one-tailed, just like before. Okay. All right, let's look at the Z statistic. Although this is very rare to be used, it is still a possibility that you could know your standard deviations for both populations. Okay, so since we are taking the HO is that this is 0. The difference between these two is 0. That's what our hypothesized difference goes here. Your estimated difference goes here. What your X bars, when you subtract them, what that is, goes here. Remember, your formula is always estimated minus hypothesized on top. Now, this value right here, for most cases with a two sample, is 0 because we're saying there's no difference. The only time that would be different would be if your problem tells you that it is hypothesized the difference between these is 20. If it tells you a difference is 20, then that's where you would write your HO as mu1 minus mu2 equals 20. And 20 would go in this spot. Okay? All right. This time, notice our populations are numbered 1 and 2 instead of A and B. I'm just trying to show you you're not stuck with the notation. You just need to make a notation and use it for that problem. Okay? Here's the weird part. Your formula for the SE, your standard error, the standard deviation of this distribution, okay, looks a little cray-cray. This is on your formula sheet for the test. You don't have to memorize these, and I'm going to show you before we close where to find these. Okay, but if you look at it, it's really not that different. You are adding the two variances together there. Remember when we did our work to find, we added variances and didn't subtract them way back at, what was that, chapter 7, I believe it is, when we were learning about sampling distributions. Okay. In the formula for mean so far for one sample, you've had sigma over n, square root of n, in the denominator. Well, that is the same as the square root of the variance over n, right? Because the square root of variance is sigma. So this formula right here, if I was on the board at the classroom, I'd be blocking off the second half. That's the same as we've been using. Now you just have to add in the second one. And the reason I can't square root this is because the square root is not going to give me just sigma back here now, because we're adding fractions there. Okay, so that's the formula for z. So let's do what about t when we don't know those standard deviations, which is more likely. Exact same thing on top. And then the only difference in the denominators is, of course, instead of sigma, we use s from the two separate samples. Okay. All right. And then after you run your t statistic, then you find your p-value just as before. You use your degree of freedom on the table, but here's the little added twist to it. Okay, if you're doing this by hand and not in the calculator, you need to figure out what degree of freedom do I use. Well, what if n of my first population is 20 and n of my second population is 30? Well, what is n minus 1? Well, you take the degree of freedom, whichever is the smaller. So I would do 20 minus 1, and my degree of freedom would be 19. The lower the degree of freedom, the more conservative I'm getting in my answer. And so we're going in the direction of being safe. Your calculator will certainly get you the exact degree of freedom and get you accuracy on this for your p-value. Okay. Once you have your degree of freedom, you of course go across the table, find the t values that your t is between, your statistic is between, and follow it up to the top and get your p-values just as we did with one sample. Okay. The calculator DF is a crazy hairy formula. If you looked through your textbook, you saw it there. You don't have to memorize that. Don't worry about it. I'm going to show it to you at the next lesson, just so you understand where it came from. But using the n1 minus 1 or the n-2 minus 1 is what we will be doing now. And of course, as n gets more and more larger, as it gets larger, we get more and more accuracy there. All right. So let's do what a confidence interval would look like. That was significance testing. What would you do for a CI? Okay, the reason I had you practicing a CI in the last one was just to kind of get our minds back on that. But that was a proportion. This is a mean. So you now have, instead of just X bar here, you have the difference of the two X bars is now what goes there. And then this new standard error formula, everything else is the same. The T star for that confidence level, again, using n minus 1, whichever one is smaller for your degree of freedom. Okay. Here's something that probably will show up on your multiple choice test. T procedures are robust here, more so than one sample T was. Okay, your robust means that you can depend on it. It's hardy. It's not affected by outliers so much. That's really the bottom line. So when the two sizes of the samples are equal and the two populations have similar distributions, these p-values are quite accurate. As n's change and your distributions change, then we do lose some accuracy, but it's pretty robust. Let's do some examples to see what the heck this is. It looks crazier than it feels. So let's just take two people video game scores, okay? And of course, this is just small data made up here to just kind of get us to talk about it. Is there evidence of a difference in the average video game scores? Remember, we don't use average as our parameter. Our parameter is mean. I still keep seeing average popping up on your tests and quizzes, but even though it asked average there, we know our parameter is mean. Okay? So your hypotheses, what would they look like in this situation? Okay? So one way you could write it, here's where I use the letters of the kids' names. Mu of Aisha minus mu of Kai is 0. Okay, there's no difference between them. This did not give us a direction for the difference, so I'm just saying not equal to 0 for my Ha. Okay? Or you can say mu of A is the same as mu of K, and mu of A is not the same as U of K. Either one of those writings is correct. So there's the no difference there versus the difference. Okay, now let's go a little further with another example. Here's Evan and Jacob flying some airplanes. Is there evidence of a difference in the distance between these two? Now it's either two samples, Evan's data, Jacob's data. Okay, these are not this is not taking all of Evan's airplanes and taking a random sampling of those. Okay, we're taking a random sampling of Evan's and a random sampling of Jacob's and comparing the two. Okay, so here's the data for these two. Okay. So of course you're going to make sure in your state that you use your symbols like I was talking about earlier. Here I just put mu of E as the true mean distance of Evan's airplane. Of course, if I knew, I didn't give whether it was meters or feet here. Okay, sorry about that, but you would if you had that given to you. Mu of J is the true mean distance of Jacob's airplane. Okay, your ho and your ha there, you can see that there was no direction of difference given. It didn't say that Jacob's flies further than Evan's. If it did, then I would have had the mu of Evan less than the mu of Jacob. But this time there was nothing like that. Just, is there evidence of a difference? So I have not equals 2 in my ha. Okay. Our conditions, of course, are terrible because this is silly little made up data. Of course, this was, nothing was given about it. But notice what I've said for both. When you're doing your conditions, you can't just say SRS given. You have to say SRS was given for both. Okay, or not given for both in this case. Normal, we got to address both. Both of these are less than 30, and so and 3 data points. We're definitely needing to proceed with caution on this. You run a graph, but that's really hard to tell anything about linear or not when you run your probability plot. So you would still do that. You'd have to run a probability plot on both. You'd have to sketch both on your test or quiz to show the picture of it, guys. Just like we did with one sample, you're doing double on your conditions, okay? And then independent, since they both have the same n, I could say here that that was less than the population for both. And on your papers, please be sure to use context, Jacob and Evan's distance, okay? Or number of planes Jacob and Evan each threw. But here's our added thing that you must throw in. Are they independent of each other? We don't know if Evan has any bearing on how Jacob's does. Maybe he's standing there making faces at him and it's causing him to not, I don't know. So what we have to do sometimes is just say it's assumed independent of each other. If you know they are, then you could state they are independent of each other. But if we're not sure, we say we're going to assume that they're independent of each other. Now here's what we got to do. We got to run one var stats on both sets of data. Get your X bars, your S's, and your N's, of course, was 3 here. Okay, and now we have that data to go to our T statistic. Okay, so I just put the formula up there to remind you. And here the difference is 0. So that's why a 0 is sitting here, because we're saying there's no difference between the two. So this is X bar minus X bar of each one, subtracting Evan minus Jacob. Okay, and then the SE, this is what you'll use on your normal curve to mark off your SEs, your standard deviations as you go towards X bar, oh boy, this right here, X bar E minus X bar J is what you're going towards on the axis now will be this number right here, your estimated value of difference. And so then you, of course, in the middle is your hypothesized on your sketch. So it'll be 0. So 0's in the middle, and then you're going towards your X bar. In this case, it's negative. So we're going to the left. Do not know why this is going on its own. That's crazy. And you get negative 8.07. Degree of freedom is 2 because our n is 3. So they're both 3. So n 3 minus 1. Going to the table, I need to write down what t is between. And then since this is 2-tailed test, I'm timesing both sides by 2. And you get your p-value to be between 0.01 and 0.02. 0.02. Okay. So this is significant at the 0.05 level because our p-value is less than 0.02, which is less than alpha at 0.05. So we reject HO and conclude there is statistically significant evidence of a difference in the average flight distances of Evans and Jacobs planes in context. And again, your sketch has 0 in the middle, your x bar 1 minus x bar 2 off on the left in this case, and then you shade to the left of that and show that the p-value is between 0.01 and 0.02. If you're going to use your calculator, I'm going to show you that later. Today, right now, we're just using the formula and understanding what it means, and then tomorrow I'll show you how to do calculator. Okay? That's it for today. So do the couple of homework problems that I have listed there for you to practice, and we will continue looking at this deeper tomorrow. Have a good rest of your day, guys.